Good afternoon, everyone. I'm Mario Facussé. I run a firm called MEF Solutions where we build revenue engines and go-to-market systems for growth stage companies. But for the last 2 years, almost everything we build has been anchored on AI automation, specifically multi-agent systems that run autonomously in production. Today, I want to teach you something that took us a long time to figure out. And I want to be upfront. What I'm going to share with you is not theoretical. This is not a framework I read in a white paper. This is a system we built, deployed, broke, fixed, broke again, and eventually got right. I'm going to show you the actual architecture, the actual data, and the actual outputs from a production system that's been running for months. The reason I want to share this is because I think most organizations are stuck in a place I call AI purgatory. And I think the way out is not what most people expect. So let's talk about AI purgatory. How many of you have deployed an AI system, a chatbot, an automation, an agent that worked brilliantly in testing and then degraded within a few weeks of production use? You're not alone. The data says about 87% of AI projects never make it past the pilot stage. And the ones that do make it to production, they require constant human intervention to stay functional. Here's what typically happens. Your team builds a prototype. It's impressive. Maybe it's a content generation system. Maybe it's a customer service bot. Maybe it's a data pipeline with LLM enrichment. The demo goes great. Leadership is excited. You deploy it. Week 1, everything works. Week 2, you notice some outputs are getting weird. Week 3, someone changes an API, or the model provider updates their weights, or your data format shifts slightly, and suddenly 30% of your outputs are garbage. So what do? You assign an engineer to babysit it. They manually tweak prompts. They add edge case handling. They become the human glue holding the system together. And now you haven't built an autonomous system at all. You've built a very expensive, very fragile machine that requires a full-time human operator. That's AI purgatory. The system is too good to shut down. It's producing value. But it's too unreliable to scale. It needs constant supervision. You're stuck. The question is, how do you get out? Here's the insight that changed everything for us. The problem is not your AI agents. The problem is that you don't have a management layer above them. Think about it this way. In a human organization, you don't just hire 22 people and let them run wild. You have management systems. You have performance reviews. You have institutional knowledge sharing. You have quality assurance. You have governance. AI agents need the same thing. And today, I'm going to teach you the 4 specific management capabilities that every production AI system needs. Number 1, shared memory. This is a system we call SEL, the shared experience layer. It's how your agents learn from each other's successes and failures, so they don't repeat mistakes and they compound institutional knowledge. Number 2, trust scoring. This is a system we call HACRL, the Heuristic Agent Confidence and Reliability Ledger. It's how you mathematically quantify which AI outputs you can trust and which ones are degrading. Number 3, prompt evolution. This is a system we call AR, autonomous refinement. It's how your systems rewrite and improve their own prompts every single week without any human involvement. Number 4, safe governance. This is a system we call AVO, the Automated Validation Overseer. It's how you let these systems deploy their own improvements without breaking production. I want to be very clear about something. These are architectural patterns, not products. You can implement them on any stack. We build ours on N8N with Supabase and Quadrant, but the principles work on LangChain, on Crew AI, on custom Python, on whatever you're using. The stack doesn't matter. The architecture does. By the end of this session, you'll have a diagnostic framework you could take back to your teams on Monday and apply to whatever AI initiatives you're currently running. To make all of this concrete, I'm going to use a real production system as our case study throughout this session. We built an autonomous content engine. It's a pipeline of 22 specialized AI agents that researches topics, develops content strategies, writes long-form articles, verifies quality, and publishes entirely without human intervention. Now, building a content pipeline is not particularly impressive. Lots of companies have done that. What's interesting about ours is not the pipeline itself. It's the factory that manages the pipeline. It's the metasystems that sit above the agents and ensure they keep getting better over time instead of degrading. Let me give you the quick architecture overview, and then we'll spend the bulk of our time on the form management systems. Here's the high-level flow. We have an asynchronous orchestrator that kicks off the pipeline. It triggers a GM researcher. That's our go-to-market researcher, which analyzes the target audience. Then a pain and dream researcher identifies the emotional hooks. A content strategist develops the angle. A content writer produces the draft. And a content verifier runs quality checks before publication. That's the pipeline. It's a linear flow with some parallelism. And honestly, if that's all we had, we'd be in AI purgatory just like everyone else. The pipeline would work for a few weeks and then start degrading. What makes this system different is the 4 metasystems that wrap around it. They monitor it, score it, teach it, and evolve it. Let me show you how we ensure quality at the pipeline level first, and then we'll go deep on the metasystems. Before we get to the 4 pillars, I want to teach you a pattern that's immediately applicable to any AI system you're running today. When you have a critical output, something that matters to your business, you should never trust a single model. In our content engine, the writing stage doesn't just call Claude and hope for the best. It uses what we call a multi-model consensus approach. We generate 3 independent drafts. Draft 1 comes from Claude 3.5 Sonnet. We prompt it for precision, dense, data-rich, citation-heavy content. Draft 2 comes from GPT 4.1. We prompt it for creativity, unique angles, compelling narratives, emotional hooks. Draft 3 comes from GPT Mini. We prompt it as an alternative voice, different structure, different approach entirely. Then we score all 3 mathematically. We calculate what we call data density, how many specific numbers, statistics, named sources, and concrete examples appear per paragraph. The highest scoring sections from each model get synthesized into the final output. Why does this matter for you? Because if you're making any important decision based on a single model's output, you're accepting unnecessary risk. The consensus pattern gives you built-in redundancy. It catches hallucinations because they rarely appear identically across 3 different models. And it produces higher quality output because you're selecting the best of 3 attempts. This is something you can implement tomorrow. You don't need a complex architecture. Just call 3 models and compare. The second pattern I want to share before we get to the metasystems is automated verification. Most companies handle quality assurance for AI outputs in one of 2 ways. Either they don't do it at all, or they have a human review every output. Neither scales. We built a 3-pass content verifier that uses different models for different types of quality checks. Pass 1 uses DeepSeek R1, a reasoning-focused model, to check factual accuracy. It verifies that every claim has a source, every statistic is plausible, and every citation actually exists. Pass 2 uses Claude for brand voice compliance. And here's the critical piece. It runs what we call an anti-AI slop detection. We have a literal banned word list. If the content contains the words delve, unleash, harness, synergy, landscape, or paradigm, it fails automatically and gets sent back for a rewrite. Because nothing screams, an AI wrote this louder than those words. Pass 3 checks SEO structure, heading hierarchy, internal linking opportunities, and readability scores. Each pass produces a score between 0.0 and 1.0. The content must pass all three to be published. If any pass scores below threshold, it goes back to the writer with specific feedback about what to fix. The principle here: define your quality criteria as code, not as vibes. If you can articulate what good looks like, you can automate the checking of it. Now let's get into the real meat of this session: the 4 metasystems that make the difference between a fragile prototype and a self-improving production system. The first system is SEL, the shared experience layer. Let me ask you a question. How does your organization handle institutional knowledge? Right? You have wikis. You have Confluence pages. You have Slack threads that nobody can find 6 months later. You have that one person who's been there forever and knows where all the bodies are buried. Now think about your AI agents. How do they handle institutional knowledge? The answer for almost every organization is they don't. Every single time an AI agent runs, it starts completely from scratch. It has no memory of what it did yesterday. It has no knowledge of what its peer agents learned last week. Imagine if every morning your entire team showed up with total amnesia. No memory of yesterday's meetings. No memory of the problems they solved. No memory of the mistakes they made. That's how most AI systems operate. And then we wonder why they don't improve. SEL solves this. It's a centralized memory system built on a vector database called HACRL that captures the experience of every agent every time it runs. Here's how it works mechanically. When an agent completes a task, let's say our GM researcher finishes analyzing a target audience, SEL logs 5 things. 1, the task intent. What was the agent trying to accomplish? 2, the model used. Which LLM did the work? 3, the reasoning trajectory. What steps did the agent take to reach its conclusion? 4, the outcome. What was the final output? 5, the quality score. How good was the output, as measured by our verification system? All of this gets converted into a vector embedding, a mathematical representation of the experience, and stored in HACRL. Now, the next time any agent in the system starts a similar task, it queries SEL first. It says, has anyone in this system solved a problem like mine recently? SEL performs a semantic similarity search and returns the top 5 most relevant past experiences. This is what an agent actually receives in its prompt before it starts working. Look at this carefully. You can see it returns experiences tagged with trust tiers. High trust means the source agent has a trust score above 0.8. Moderate trust is between 0.5 and 0.8. Low trust is below 0.5. The agent knows how much to weight each piece of advice. You can see the similarity percentage, how closely this past experience matches the current task. In this example, the top result is 87% similar. You can see the reasoning trajectory, the actual steps the previous agent took. Not just what it produced, but how it got there. And look at the instruction at the bottom. Adapt rather than copy. Use these experiences as context, not as templates. We explicitly tell agents not to blindly repeat past actions. We want them to learn principles, not memorize answers. Here's a critical design decision that took us a while to figure out. We exclude the requesting agent's own past experiences from the search results. Why? Because we want to force cross-pollination. We want the content writer to learn from the GM researcher's approach to structuring information. We want the content strategist to learn from the verifier's quality criteria. If agents only learn from themselves, they get stuck in local optima. Cross-agent learning is where the real breakthroughs happen. Now, let me ask you, how many of you have more than one AI agent or workflow running in your organization right now? And how many of those agents share knowledge with each other? That's the gap. If you have multiple AI systems and they aren't building shared institutional knowledge, you're leaving massive efficiency gains on the table. Every agent is solving the same problems independently over and over again. Shared memory is powerful, but it introduces a new problem that most people don't think about until it bites them. If agents are learning from each other's experiences, what happens when one of those experiences is wrong? What happens if an agent hallucinates, produces garbage output, and that garbage gets stored in the memory bank? Now, every other agent that queries SEL might retrieve that hallucination and treat it as reliable guidance. You've essentially built a system where bad information can spread like a virus through your entire agent swarm. This is why you need the second system, HACRL, the Heuristic Agent Confidence and Reliability Ledger. HACRL answers one deceptively simple question: how much should I trust this specific agent? Right now, today, in most organizations, trust in AI systems is subjective. Someone says, the research agent has been acting weird lately, or I think the writer's quality has dropped. That's not good enough for production. You need a number. You need a quantitative, continuously updated metric that tells you exactly how reliable each component of your system is at any given moment. HACRL provides that number. It runs automatically every 6 hours. It pulls up to 5,000 recent execution records from our database, and it recalculates a trust score for every single agent in the system. Here is the actual formula we use. I'm going to walk you through it because the design decisions matter. The trust score is a weighted composite, 40% weight on recent 7-day quality. This is the most heavily weighted factor because it catches degradation early. If an agent was great last month but terrible this week, the trust score drops fast. 30% weight on all-time average quality. This provides stability. A single bad day doesn't destroy an agent's reputation if it has a long track record of excellence. 30% weight on success rate. This is binary. Did the workflow complete without throwing an error? An agent that produces mediocre content but never crashes is more trustworthy than one that produces brilliant content 70% of the time and errors out the other 30%. Then we multiply the whole thing by a confidence multiplier, the minimum of total executions divided by 20 and 1.0. What does that mean? It means a brand new agent that's only run 3 times doesn't get a full trust score. It needs at least 20 executions before we have enough data to trust the score itself. This prevents a new agent from getting a perfect score based on 2 lucky runs. Here's what a real trust score record looks like. You can see the agent's name, the trust underscore score, 0.847 in this case, the capability underscore ratio, the success rate, and the average underscore quality underscore recent. All of this is queryable, trackable over time, and critically, it cascades directly back into SEL. Remember those trust tiers I showed you? High, moderate, low? Those come directly from HACRL. When an agent's trust score drops below 0.5, its past experiences in the memory bank get tagged as low trust. Other agents still see them, but they know to treat that information with skepticism. If the trust score drops below 0.3, those experiences are effectively quarantined. The system self-prunes bad data before it can infect the rest of the swarm. This is the immune system of your AI architecture. Without it, one bad agent can poison the entire collective memory. All right, we have agents that share memory. We have a system that quantifies their reliability. Now we need them to actually get better over time. Let me ask you something. How do you currently improve your AI prompts? Right? Someone on your team, maybe a prompt engineer, maybe a developer, maybe a product manager, sits in a UI, tweaks some words, runs a few tests, and deploys the change. Maybe they do this once a month, maybe once a quarter, maybe only when something breaks. That's manual prompt engineering. And it has three fundamental problems. First, it doesn't scale. If you have 9 agents with complex prompts, you cannot manually optimize all of them simultaneously. You'll always be behind. Second, it's reactive. You only improve prompts when you notice a problem. But degradation is often gradual. By the time a human notices, you've been producing suboptimal output for weeks. Third, it doesn't compound. When a human tweaks a prompt, they rarely document why the change worked. The next person who touches that prompt doesn't know the history. You lose institutional knowledge about what makes prompts effective. AR, autonomous refinement, solves all three problems. It completely automates prompt engineering across all 9 of our core agents. Here's how it works. Every week, on a cron schedule, AR wakes up and looks at each agent. It fetches the agent's current active prompt from our database. Then it passes that prompt to Claude Sonnet 4 with a very specific instruction. Generate a mutated version of this prompt that is likely to improve the agent's performance on its primary KPI. AR uses 6 specific mutation strategies. It doesn't just randomly change words. It applies structured techniques. 1. Clarify instructions. Make ambiguous directives more specific to add constraints. Introduce guardrails that prevent common failure modes. 3. Restructure flow. Reorder the prompt sections for better logical progression. 4. Reduce ambiguity. Eliminate phrases that could be interpreted multiple ways. 5. Add examples. Include few-shot demonstrations of desired output. 6. Simplify language. Reduce complexity to improve model comprehension. The mutation generator picks the strategy most likely to address the agent's current performance gap. But here's the critical thing. AR does not deploy mutations blindly. It runs a controlled experiment. It takes a standardized test input and runs it through the baseline prompt, the current production version. Then it runs the same input through the mutated prompt. Both outputs go to an independent LLM judge. We use Gemini Flash for this, which scores them on a 0.0 to 1.0 scale for the agent's primary KPI. The judge doesn't know which output came from which prompt. It's a blind evaluation. Here's a real experiment log from our GM researcher agent. Look at this data. The baseline prompt scored 0.72 on data completeness, our primary KPI for the researcher. The mutated prompt scored 0.89. That's a delta of plus 0.17, a 17 percentage point improvement. The mutation strategy was @_constraints. What did it actually change? It added a specific instruction requiring the researcher to always include company size, funding stage, and tech stack in its output. A simple, targeted constraint that dramatically improved completeness. The status shows winner_promoted, meaning AR automatically updated the production prompt to the new version. Now here's where it gets interesting. This happens every week. For every agent, the improvements compound. Week over week, the prompts get incrementally better. After 3 months of AR running, our average content quality scores increased by over 30%, with 0 human prompt engineering. And because every experiment is logged, the mutation strategy, the rationale, the scores, the outcome, we're building a knowledge base of what works in prompt optimization. The system is learning how to learn. Let me also mention something important about how AR and AVO interact. AR manages prompt evolution for the 9 core content agents. But AVO, which we'll talk about next, handles optimization for infrastructure workflows. They have a deconfliction protocol. Before AVO proposes a change to any workflow, it cross-references with AR to check if that workflow already has an active experiment running. If it does, AVO defers. They don't step on each other's toes. Now we arrive at the system that keeps everything from blowing up. If you've been following along, you might be feeling a bit nervous. We have a system that rewrites its own prompts. We have a system that shares experiences across agents. We have trust scores that automatically quarantine bad data. There's a lot of autonomous behavior happening here. And the natural executive question is, what happens when something goes wrong? What happens when mutation makes things worse? What happens when a deployment breaks a webhook? What happens when the system optimizes itself into a corner? This is the job of AVO, the Automated Validation Overseer. AVO is the grand supervisor. It sits outside the pipeline, watches everything, and has the authority to intervene, block, and roll back. Think of it as the combination of a monitoring system, a deployment pipeline, and a circuit breaker, all in one. AVO has 4 major responsibilities. 1. Diagnostics, continuously monitoring system health and identifying problems before humans notice them. 2. Prompt evolution for infrastructure, proposing optimizations to non-content workflows, the plumbing, not the content. 3. Safe implementation, deploying approved changes with a full safety protocol. 4. Rollback, instantly reverting changes that cause problems. Let me walk you through each one. Every morning at 3:30 a.m., AVO's diagnostics engine wakes up and runs a comprehensive health check on the entire system. It queries our database for all executions in the last 24 hours. It pulls KPI snapshots. It identifies declining or stagnating metrics. It checks for unresolved critical errors. Then it compiles all of this into a context package and sends it to Claude with a specific instruction. Analyze this system's health. Identify the top issues. Propose specific optimizations with priority levels. This is the actual Microsoft Teams message that drops into our channel every morning. Look at what it contains. System health score, a single number that tells me at a glance whether things are fine or on fire. Success rate, what percentage of workflows completed without errors. Average execution time, is the system getting slower? Cost, how much did we spend on API calls yesterday? Top failing workflows, which specific workflows are having problems? Optimization proposals, specific, actionable suggestions with priority levels, P1, P2, P3. As an executive, I glance at this every morning with my coffee. If the health score is above 0.85, I move on with my day. If it's below that, I look at the proposals and decide whether to approve them. That's the key insight. The system surfaces its own problems before humans notice them. I'm not finding out about issues from angry customers or confused team members. The system tells me proactively, with a proposed solution already attached. When I approve a proposal, or when AVO's prompt evolution engine generates an infrastructure optimization, the implementation engine takes over. But it does not just blindly deploy changes to a live production system. Before any modification touches the production in 8-in instance, AVO runs a gauntlet of 6 safety checks. Check 1. LLM self-assessment. The implementation LLM must confirm that its proposed changes are safe and reversible. If it expresses any uncertainty, the deployment is blocked. Check 2. Credential integrity. Did the modification accidentally delete, modify, or expose any API keys, tokens, or credential references? If any credential node is altered, blocked. Check 3. Webhook preservation. Did the modification break any webhook triggers? Webhooks are the entry points to our workflows. If they change, nothing can trigger the workflow anymore. If any webhook is altered, blocked. Check 4. Node count delta. If the proposal was to add a retry loop, but the LLM generated 20 new nodes, something went wrong. We enforce a maximum delta of 5 nodes. If the modification adds or removes more than 5 nodes compared to the original, blocked. Check 5. Workflow name preservation. The workflow name must remain unchanged. This sounds trivial, But if the name changes, all of our monitoring, logging, and KPI tracking breaks because they reference workflows by name. Check 6. Error handler preservation. Every workflow has error handling nodes that report failures back to AVO. If the modification removes or alters these error handlers, the system would lose visibility into failures. Blocked. Before any of these checks even run, AVO takes a full JSON snapshot of the production workflow and stores it in Supabase. This is the restore point. If anything goes wrong after deployment, the rollback guardian can instantly revert to this exact snapshot. And here's the circuit breaker. If a workflow has been rolled back 3 times, AVO locks it down completely. No more automated changes are allowed. It escalates to a human engineer with a message that says, essentially, I've tried 3 times and I keep making it worse. You need to look at this. That 3-strike rule is critical. It prevents the system from getting into an infinite loop of deploy, break, rollback, deploy, break, rollback. It knows when to stop and ask for help. Now, I've explained each system individually, but the real power, the thing that makes this architecture fundamentally different from a static AI pipeline, is how these 4 systems interact with each other. Let me walk you through the flywheel. AR runs an experiment on the content writer's prompt. The mutation wins. The new prompt is deployed. Now the content writer produces better output. Because the output is better, the content verifier gives it higher quality scores. Those higher scores flow into HACRL's trust calculation. The content writer's trust score increases. Because the trust score is higher, when SEL retrieves the content writer's past experiences for other agents, those experiences are now tagged as high trust. Other agents weight them more heavily. The entire swarm gets a little bit smarter. Meanwhile, AVO is watching the KPI dashboard. It sees that content quality has improved, but it also notices that execution time has increased by 12% because the new prompt is more complex. So AVO proposes an optimization to streamline the workflow's data passing. I approve it. Execution time drops back down. The cycle repeats. Every week. Automatically. This is the compound interest of AI systems. Each improvement makes the next improvement more likely and more impactful. After 6 months, the system is dramatically better than it was on day 1. And no human had to manually tune anything. Compare this to the typical approach. Deploy an AI system, watch it degrade, manually fix it, watch it degrade again. That's linear. What I'm describing is exponential. All right, let's bring this back to you and your organizations. I've shown you a specific implementation, but the principles are universal. When you go back to your teams, I want you to look at your current AI initiatives and ask these 4 diagnostic questions. Question 1, memory. How are our AI agents sharing what they learn? If the answer is they don't, and for most organizations, that's the honest answer, you are wasting compute. Every agent is independently solving problems that other agents have already solved. You need some form of shared experience layer. Question 2, trust. How do we quantitatively measure AI output reliability? If the answer is we spot check it, or we have a human review samples, you cannot scale. You need a continuous, automated trust scoring mechanism. You need a number that tells you, at any moment, how reliable each component of your system is. Question 3, evolution. How are our prompts improving over time? If the answer is our engineers tweak them when something breaks, you are moving too slowly. Your competitors who automate prompt optimization will compound improvements weekly while you compound them quarterly. Over a year, that gap becomes enormous. Question 4, governance. What happens when an autonomous change breaks something? If the answer is users complain and we scramble to fix it, you are carrying unacceptable risk. The faster your systems move, the stronger your safety nets need to be. Build a rollback capability before you need it. Now, I don't want you to leave here feeling overwhelmed. You do not need to build all 4 systems simultaneously. That's what we did, and honestly, it was painful. Let me save you some pain. Here's the sequence I'd recommend. Start with trust scoring. This is the lowest effort, highest visibility win. Just start measuring the quality of your AI outputs systematically. Even a simple scoring rubric that runs after every execution gives you visibility you didn't have before. Once you can see degradation happening, you can respond to it. Then, add shared memory. Once you're scoring outputs, you have the data to build a memory system. Log the high-scoring executions. Make them retrievable. Let agents learn from the best examples. Then, add prompt evolution. Once you have scoring in memory, you have the infrastructure to run experiments. You can measure whether a mutation actually improved things. Without scoring, you're flying blind. Finally, add safe governance. Once your system is evolving autonomously, you need the safety nets, the rollback capability, the deployment checks, the circuit breakers. Each layer builds on the previous one. You can implement each in roughly a 90-day sprint. In a year, you have the full architecture. Let me leave you with 5 things to remember from this session. 1. Production AI requires management systems, not just better prompts. The agents are not the hard part. Managing the agents is the hard part. 2. Self-improving systems compound their gains over time. Like compound interest, the earlier you start, the more dramatic the long-term results. 3. Safety and governance are prerequisites for autonomy, not afterthoughts. You cannot move fast if you can't roll back safely. 4. These are architectural patterns. They are stack agnostic. Implement them on whatever platform you're already using. 5. Start with measurement. You cannot improve what you cannot measure. Trust scoring is your foundation. Thank you. That's the end of the structured content. We have about 30 minutes for questions, and I'd love to go deep on any of these systems. If you want to continue the conversation after today, you can scan the QR code on the screen to connect with me on LinkedIn. I'm always happy to talk shop about multi-agent architectures, autonomous systems, and the operational challenges of running AI in production. What questions do you have? Question: what's the cost of running all these metasystems? A. The 4 metasystems add roughly 15 to 20% overhead to our total API costs. But they've reduced our manual engineering time by over 80%. The ROI is not even close. The systems pay for themselves many times over. Question: how do you handle the cold start problem? When you first deploy, there's no memory and no trust data. You bootstrap it. For the first 2 to 3 weeks, you run the pipeline normally and just log everything. You build up the experience database and trust scores passively. Then you flip on the retrieval and evolution systems once you have enough data. The confidence multiplier in HACRL handles this gracefully. It won't give full trust scores until there are 20+ executions. Question: what happens if the LLM judge an AR is wrong? It happens. That's why we don't promote a mutation based on a single evaluation. We require a statistically significant margin. And even after promotion, HACRL is watching. If the new prompt causes quality to drop over the next week, the trust score will decline, and AVIO will flag it in the next diagnostics report. Question: can this architecture work for non-content use cases? Absolutely. The patterns are domain agnostic. We've seen similar architectures applied to customer service bots, data enrichment pipelines, code generation systems, and financial analysis workflows. Anywhere you have AI agents that need to improve over time, these principles apply. Question: how long did it take to build? The initial pipeline took about 6 weeks. The 4 metasystems took another 4 months of iteration. But most of that time was learning what didn't work. With the patterns I've shared today, you could build the core architecture in 8 to 12 weeks.